Hello everyone. Today I'm going to talk about Bezout theorem and branch of the form x squared plus ny squared. First of all, I would like to thank my mentor Bezout for his contribution and also the organization. We will have two parts. In the first part, we have some definition and Bezout theorem, and the second part includes branch of the form and quadratic forms. And algebraic geometry. Algebraic geometry is concerned with zero sets of polynomials. For instance, if you have polynomial f xy, which is equal to x minus y squared, this zero set of this polynomial is equal to this figure, which is parabola. And roots of fx, the intersection of y minus f and y equal to 0, leads us to this question: how many intersection points should two curves have? And Bezout theorem helps us to determine the number of intersection points between two algebraic curves. And since we don't know what is algebraic curve, we will give some definitions. The projective plane is the set of equivalents of triples such that which are not zero. And for some non-zero t, if two triples are in relation, we have these equalities, and we call A, B, C are homogeneous coordinates. And the usual Euclidean plane, also called the affine plane, is pairs, which are the set of pairs which are numbers. And line projective plane, the set of points A, B, C, which satisfy this equation, where coefficients are not all zero. And the algebraic curve in the affine plane is the set of polynomials, the set of solutions to polynomial fx, y in two variables. And here's the example for algebraic curves. The first one is the circle, the second one is the parabola. And a polynomial f is called homogeneous of degree b if satisfied this equality for any t. And equality phase f is linear combination of monomials degree d, and projective curve c of degree d is the zero set of non-constant polynomials, homogeneous polynomials of degree d. And here's another example. This curve c1 has degree 2 and the c2 has degree 3. And if we have two curves C1 and C2, which are defined by F1 and F2, then their intersection is the set of solutions to both polynomials, F1 and F2. And here's another example. If we have a curve which has degree 2 and another curve which has degree 4, they should intersect in 8 points. And we call C1 and C2 have no common components if there is no polynomial P that divides C1 and C2. And here's intersection index. If we have two curves with non-common components and point P in the projective plane, then intersection index of C1 and C2 at P satisfies one of three conditions. If point is in the intersection, is not in the intersection, then the intersection index is equal to 0. If C1 and C2 have distinct tangents at P, then intersection index is equal to 1. And we can say that C1 and C2 intersect transversely at P. And if C1 and C2 have same tangent at P, then their intersection index is greater than or equal to 2. And here's Bezout theorem. If we have two curves C1 and C2, projective curves with no common components, then their intersection points at P is equal to product of their degrees. And if C1 and C2 intersect only transversely, then the number of intersection points is equal to product of degrees. And in all cases, we have this fact: the number of intersection points is bounded by the product of degrees. And here's corollary about the theorem. If you have intersection points, if C1 and C2 has intersection points is equal to n square and their degrees are n. If we have another curve, irreducible curve D, which mn points are on the D, and the remaining points lies on a curve which has degree n minus 1. Here's the proof. We have two curves, which is defined by F, the other one is defined by G, and we have irreducible curve D, which is defined by H. And if D is a component of C1, then we can define F as HL, and H contains the rest of the points. And if D is not component in C1 and C2, we have P, which is in D out of C1 and C2. Then we have this curve, defined as this equation. And we have mn points from D, n plus the point P. And by using Bezout theorem, C and D have common component. And so D is component of C. And the equation is HL prime for some polynomial L prime. And since intersection is component of C, and we have already mn points on D, the rest of points are on L prime. And I will continue with the second part of this presentation. We have this question. Can we define which primes can we define expressed as this expressed as x square plus ny square? And for the case that n is equal to 1, we have this following theorem. N of prime p can be written as x square plus y square if and only if p is equal to 1 mod 4. And for the later use, we need the definition of Legendre symbol. Legendre symbol of A, where A is integer, at P is defined as this condition. If P divides A, then this symbol is equal to 0. And if P does not divide A, and we have some integer which is equivalent to A is where A is equivalent to x square mod P, then it's equal to 1. If P does not divide A, and we cannot find such integer x which satisfies this equation, then this is equal to minus 1. And here's an example. 1, 3, 4, 5, and 9. At 11, their Legendre symbols equal to 1. And the other 2, 6, 7, 8, and 10 is equal to minus 1. And here's some properties of Legendre symbol. If we have two integer equivalent under same mode, P, then their Legendre symbol are equal. If we have some square at P, then this is equal to 1 if P does not divide A. And the product of two integers at P is equal to distinct product of Legendre symbols. And 1 at P is equal to 1, and minus 1 at P is equal to this number. And by using Fermat's theorem, we have these cases. Negative 1 at P is equal to 1 if P is equivalent 1 mod 4, or minus 1 if P is equivalent 3 mod 4. And since we have this lemma. If we write P as a form of x square plus ny square, this happens if and only if the Legendre symbol of negative n must be equal to 1. And here's the proof. If P divides x square plus ny square, and this means that this is equal to 0 mod P. And from the assumption of the lemma, since we know that a greatest common divisor of x and y is equal to 1, P does not divide y. So y has an inverse in quotient, and negative n is equal to x a square mod P. Since P also does not divide n, we have this equality. On the other hand, if my negative n is equal to x squared mod p for some integer x, then p divides x squared plus n. We will continue with quadratic forms. A quadratic form of is a polynomial ax squared plus bxy plus cy squared, where all coefficients are integers. And we say that if you have two quadratic forms, we say they are equivalent if there are integers p, q, r, s that satisfy this equality. And if and also we have p s minus qr is equal to plus n minus 1. If this is equal to 1, then we say that f and g are properly equivalent. And here's theorem about equivalent quadratic forms. If we have two equivalent quadratic forms, if m is represented by f, it also must be represented by also g. And if they have to same discriminant. And if f is primitive, g must be also primitive. And if you have integer m and quadratic form f, then m is properly represented by f. If and only if f is properly equivalent to this quadratic form for some b integers b and c. And here's lemma. If we have discriminant d equivalent to 0, 1 mod 4, and let m is an integer, odd integer, relatively prime to d, then m is properly represented by primitive form of discriminant d, if and only if d is quadratic residue modulo m. Here's the proof. If fx represents the m, then by previous lemma, we know that f is properly equivalent to this form. And by using that, and we know that discriminant is equal to b squared minus 4mc for this form, and d is equal to b squared mod m. And conversely, if d is equal to b squared under modulo m, since m is odd, and as let's assume that d and b have the same parity, then d is equal to 0, 1 under mod 4. That implies that d is equivalent to b squared mod 4m. That is equal to this discriminant. And since this represents m and has discriminant d, and we know that coefficients are relatively prime, and since we assume that m is relatively prime to d. And as a last theorem, if we can express primes of the form x plus ny squared with quadratic forms, let an integer and p odd prime not divide d, then the legendary symbol is equal to 1 if and only if p is represented by primitive form of discriminant minus 4m. And the proof comes from this lemma, and this comes from previous lemma, and the proof is done. Here's my references.
Okay. Thank you, Mustafa, for the talk. Any questions from the audience?